All right, welcome back. Mech 1330 Fluid Power. We're getting into Chapter 11 in your book, Pneumatic Power Supplies. All right, so let's talk about what they are. Okay, compressors. All right, we got to compress air, right? So that's our power supply, essentially. You know, kind of how electrical has a battery, mechanical has a motor, those different things. All right, so for pneumatics, we have to have a compressor somewhere. We've got to be getting our compressed air from someplace, okay? So let's talk about cycling a compressor. So when the pressure drops to a predetermined minimum in a tank, the compressor is going to automatically kick on, all right? And you can use that with a valve or a gauge or things like that to where you set it to. So the cut-in pressure, that's the pressure at which the compressor turns on. The cut-out pressure, okay, that's the pressure at which the compressor turns off. All right, so you might have cut-in. So anytime it drops below 90 psi, you might have it cut on, all right? And then you might have it fill the tank up to like 120, 150 psi and have it cut off, okay? Cycle a compressor, okay? That's controlled by the pressure switch, which senses the max and min pressure that I was talking about, the 90 and the 150 or so, okay? So if starting and stopping the prime mover is not practical for the situation, okay, because it can cause damage, we have two options here. We can use a clutch, all right? We use that to disengage the motor from the compressor when the cutoff pressure is reached, or we can use valves, right? We can discharge the outlet flow to the atmosphere when the cutoff pressure is relieved, okay? So sometimes you'll hear a compressor kick on, and we'll just keep venting into the atmosphere, things like that. Okay, different types of compressors that you can buy, all right? And the next few slides are all going to be reviewed from a previous chapter in hydraulics. So I'm going to kind of go through these fairly quickly when we go through this, okay? A positive displacement pump. So we operate that by opening up a cavity to draw in fluid, and then the cavity expels the fluid when we close it, okay? So there's a gear type or a piston type. So the three designs are the reciprocating piston, the rotary vein, and the rotary screw. Okay, so just a picture of what the reciprocating piston, and remember this is all review. It's the most common design for a small to medium-sized commercial compressor. Consists of one or more pistons. Okay, so as the crankshaft rotates, the pistons reciprocate, drawing in the atmospheric air and pushing out the compressed air. I mean, think of yourself on one of those old school like red bicycle pumps. All right, where you're pumping, you're pulling the pump up, all right, and pushing it down to evacuate the air into your bike tire. Okay, rotary veins, we've talked about these as well. As a rotor spins, the veins are kept in contact with the housing by centrifugal force, right, that rotational force, causing them to extend and retract, and that extending and retracting, okay, that makes the chamber between the veins increase or decrease in volume near the inlet and outlet, right? So we, as we increase, right, those veins drop down, rotates around, and it creates a vacuum in the inlet, okay, which lets the atmospheric air push into the inlet. And then the volume at the outlet decreases as we exhaust the air into the tank, okay? Rotary screw, all right, we're compressing air between the intermeshing screws, okay, capable of generating up to 150 psi. These are the most common ones we use in industrial applications, okay? Non-positive pump, all right, that imparts a velocity to a fluid, so we add it, right? Okay, remember non-positive might be varying or things like that. The centrifugal type, we're using an impeller to spin the fluid and increase its kinetic energy. A diffuser, we're converting the kinetic energy to pressure energy, okay, and we can have a single stage or multi-stage designs, generate low pressure, high flow when we do these. All right, so let's do some calculations, or get some equations in, then we'll do a few examples. All right, so when we want to size the compressor, look, if you notice there, the compressor is sitting on top of the tank, all right? Generally, the compressor is really right at the tank, most of the time on top of the tank, whether it's a horizontal tank like the one you see here or a vertical standing tank, okay? So we size it to supply sufficient pressure to a system under all expected conditions, as well as it to remain idle for part of the cycle. So we include the motor, the compressor, and the receiver tank. All right, the receiver tank in the picture here is the yellow tank piece that we're going through there, okay? So we want to be able to calculate the required power, so you guys can write down that equation right there. The top one, obviously, imperial units, bottom one, metric units. Okay, so let's do the sizing here. We want to determine the input power required to drive a compressor that delivers 200 standard cubic feet per minute at 120 psi gauge. The overall efficiency of the compressor is 70%. Okay, so we're going to use the equations on the previous slide. But first and foremost, right, we have to be in absolute pressure when we do these calculations. So we're going to start out at 0. We have to add 14.7. Okay, we want to end up at 120. Okay, so we have to add 14.7 to that. So we use these two as our absolute pressures. Okay, and we substitute everybody in here to the equation. All right, run through everything, and we roughly get the input power needs to be 56.7 horsepower. So I'd probably have like a 60 horsepower motor, maybe something a little bit bigger if we size it up. Okay, make sure we're using the eta efficiency. We're using 0.7 when we substitute that in. All right, same kind of calculation going on here, only we're doing a metric example. So we want to determine the input power required to drive the compressor, delivering 5.7 standard cubic meters per minute at 830 kPa with an overall efficiency of 75%. Okay, so we still have to take our pressures and add the 101. We have to add the atmospheric pressure like we did all last chapter. Okay, to do these calculations for our input and our output pressure. Okay, our input, right, if we're starting at 0, we're going to do 0 plus 101 kPa, and that worked in the previous example as well. Okay, and then in this one, we want to end up at 830. We got to add 101. So we have to do all of our calculations in absolutes. So now we're going to calculate the input power. Okay, we're just substituting into the equation. Now we're using the metric one because we want kW. Substitute in all these numbers. I know those look like some funky brackets. I was having a little trouble here with the equation editor on PowerPoint, but those are brackets, those funky line looking things on the equation here. So hopefully that answers your question. Just use a bunch of parentheses. Make sure your calculator, do stuff using order of operations. Put numerators in parentheses, denominators in parentheses when you're doing multi-steps with addition or subtraction, multiplication, and division. Okay, so we want to calculate the size of the tank. Okay, so what we just talked about was, you know, if I step back, we want to size the compressor. Now we want to actually size the tank. All right, so we want to be able to manage the tank so that it can supply to, you know, our usage at the same time, not make the compressor run the entire time and still have a supply in it. Okay, so when we size the tank, we determine how much air we can store in the tank. So you can write down those two equations. The top one is for imperial units. The bottom one is for metric units. You can easily tell that too, right? Because we have 14.7 on the top, which is atmospheric pressure in imperial units, and we have 101 on the bottom, right, which is atmospheric pressure for metric units. Okay, so there's kind of how you keep track of the two equations. The equations are the same other than those two values. All right, so let's do an example here. We got a compressor unit. It's required to provide a flow of 50 standard cubic feet per minute to a system for 10 minutes while the compressor sits idle. Okay, what size receiver tank is required? The system has to operate between 125 and 90 gauge pressure. Okay, so important to understand the system here. First, we know that we are in imperial units, okay, because we're in standard cubic feet per minute, and we have our readings in PSI. Okay, so when we substitute this in, okay, for the tank size, we literally substitute in all of our values. Okay, now, the thing I didn't talk about too much on the previous slide that I'm going to talk about more on this one, okay, Q demand, Q delivery. Okay, so demand means, you know, what we're using for drawing from the system. So the compressor unit, we're providing the flow of 50 standard cubic centimeters. There's no demand. Nobody's using it right now. So that's why our deliver to the system is 0. So right now we're just filling the tank. We're not using the tank at the same time. Okay? So the next part here, using the tank above, determine the time to recharge the receiver tank from 90 to 125, okay, PSI gauge if the compressor delivery flow is 100 standard cubic feet per minute. Assume the demand remains constant at 50 standard cubic feet per minute. Okay? So now we're using it and we're filling it at the same time. All right? So, there's a bunch of people using it, tools along the line, and we're filling the tank at the same time. Okay? If we solve the original equation, okay, for T, algebraically, and I can do that on the board for you in class when we go through this. All right? And then substitute in our given values, it's going to take us approximately 5 minutes to recharge this tank when we're filling it and using it at the same time. Okay? We have to deliver 150. Our demand is 50. All right? We're using it at the same time as we're filling it. So that's why it takes 5 minutes. Okay? The only reason we switch demand and delivery is to avoid the negative. All right, it represents the flow, the direction flow, but for us, for time-wise, all right, we're not going to do negative time. All right, next let's talk about vacuum pumps. Okay, vacuum pumps evacuate air from one side of an object, allowing atmospheric pressure to act on the opposite side. Okay, they're just like air compressors, only they work in reverse. And most compressors, or not compressors, vacuum pumps are rotary vein type. And if you remember when we talked about vacuums previously in the hydraulic piece a little bit, we talked about a venturi, right, where we shrunk the throat down. All right, so flow remained the same, okay, but our velocity increased, which helped us create that vacuum. All right, so we're actually able to suck. Okay, so venturi, that's a pipe with a reduced diameter section in the middle. We call that the throat. Okay, we use that throat so that the pressure drops below atmospheric pressure, creating a vacuum. I'll show you a cool video we have in class where we actually, not we as in our class, but there's a cool video where you can compress a full train car by dropping it below atmospheric pressure and watching it get crushed by the atmosphere. But essentially, we connect that vacuum port to a suction cup, and we are able to lift things up like we do on our 870 Trainer Station 1. Okay, so vacuum pumps, when we kind of break it down, why use them? Okay, we can put them on existing pneumatic systems. They're reliable, and we don't have to add any lubrication to them, generally making them maintenance-free when we use them. You can kind of take a look here at, on the right-hand side, what it really looks like. Okay, that's a vane pump, obviously. As you see impeller, not vane, but you can see the impeller, all right, as it rotates around, sucks everything in, adds a velocity to it, and discharges it back to the pump when we're doing it. Well, that is the end of Chapter 11, okay, when we're talking about compressors, the receiver tank, the compressor itself, and vacuum pumps. If you have any questions, feel free to email me, guys. Else, I'll talk to you in class if you got anything. See you in class. Have a great day.